So I think I stopped yesterday at this slide. So we're back to magnetars, okay? Neutron stars with ultra-strong magnetic fields. And so I showed this slide where you can see that magnetars are hot. Okay, so they have thermal luminosities exceeding 10 to the 35 ergs per second, which is roughly 100 solar luminosities. And just from these observations, magnetars here are shown in red. I hope you can see something on the... Not really, right? You see something red and some black curves, but... Yeah, I mean... Yeah, they're hot, yeah. Yeah, I don't know if it's just this slide or this is... let's see the other slide. Okay, I guess I have no choice anyway, so we'll just keep going.
You can use the blackboard.
I can draw the data sets and then... Okay, all right, so they are hot, and there must be heating source inside the star. Now, when you look at the stellar interior, what do you see? Well, you see a liquid core, which is 10 kilometers in radius, and this core is bounded by a solid crust, which is about 1 kilometer thick. So it's rigid material, like Coulomb lattice, mostly, except for the ocean on the surface, which is liquid, and the atmosphere above the ocean. So the heating source, in principle, could be anywhere inside the star. And your first natural assumption would be that, okay, there must be something going on in the core. The core is hot, unusually hot, compared to other normal neutron stars, not magnetars. You can quantify this kind of expectation if you solve a simple steady-state problem when you assume certain temperature in the core. And by the way, it has to be isothermal, because the thermal conductivity inside neutron stars is huge. So if you heat a region in the core, you immediately, the thermal conduction, heat conduction will immediately distribute this heat. And so the core is kept very close to isothermal conditions. Now, you assume a certain temperature in the core, and then you can calculate the simple steady-state heat transfer problem where the heat steadily diffuses to the surface and is radiated from the surface. Of course, for that, you need to know the thermal conductivity. That's the one thing you need to know if you want to solve a heat conduction problem. And in simple spherical symmetric geometry, you can write the standard heat conduction equation, so it's quite a nice problem. Just you need to know the conductivity. Fortunately, it was calculated in great detail, in particular by St. Petersburg group, in particular Potechin. They've done nice calculations in great detail of all the parameters, including thermal conductivity of the crustal material. Now, crustal material is particularly interesting because the blanket where the main gradient of temperature occurs is in the crust. So the core is isothermal because of huge conductivity, and then as you approach the surface, there is a drop of temperature by a couple of orders of magnitude. Just because the crust, well, it also has huge conductivity, but smaller than in the core, in particular the upper crust. Of course, the heat is conducted by electrons, which are degenerate. So, at finite temperature, you have phonons in the lattice, okay? And so electrons experience some resistivity. So the same process, basically the finite free path of electrons, controls both electrical conductivity of the crust and thermal conductivity. They are related, of course. There is a relation between these two quantities, because both are determined by the free path of the electrons. Right. So anyway, I'm not going to review these calculations. It's done. It's very well known, and so one can solve that problem. Let me just show the result. So this plot shows what surface luminosity, black body surface luminosity you get at the surface. You can translate it to a temperature, effective temperature of that emission from the surface. Again, sigma t to the fourth times 4 pi r square is the luminosity, right? So the heat flux that goes from the core is just converted to sigma t to the fourth at the surface. And so what is shown here is this total flux integrated over the area of the star versus the core temperature. And the temperature shown is in units of 10 to the 8th Kelvin. This kind of characteristic temperature of neutron stars of this kiloyear age. Remember, magnetars are roughly kiloyear old. And, but they are hotter than 10 to the 8th, and they may have temperature up to 10 to the 9th Kelvin. So that's the range here, from 1 to 8 times 10 to the 8th K. And so you can see that if the temperature is approaching 10 to the 9th Kelvin, then you can get the thermal luminosity that you actually observe from the surface, 10 to the 35 ergs per second. The exact result depends on the composition that you assume in the upper crust. You could assume just iron, which is the ground state material, or you could assume that there are some light elements, and the result will depend on that because the thermal conductivity depends on chemical composition. All right, so one conclusion you can make from this plot that if magnetars are hot because there is heat flux from the core, this core has to be really hot, 10 to the 9 Kelvin in temperature. Another piece of information in this plot is this neutrino ceiling on the right. It turns out that when you solve this heat conduction problem, you also have to take into account energy losses due to neutrino emission in the crust. So if you have a star, the heat diffuses to the surface, comes to the crust. Here there are reactions that can, of course, there is also neutrino cooling in the core, but also there is a minimum neutrino cooling that you can calculate accurately that steals part of this heat flux. And so if your temperature, internal temperature of the core and the inner crust approaches 10 to the 9th Kelvin, there is a neutrino ceiling essentially for the outgoing flux because any excess would be stolen by neutrino emission. Neutrino emissivity is very sensitive to temperature. And so when temperature is 10 to the 9th, neutrino losses go so high that that they just remove all the heat flux and it doesn't reach the surface essentially. So there is a ceiling which is remarkably close to the characteristic flux of heat that we observe from magnetars. The total luminosity would be 10 to the 35 ergs per second. So that was quite suggestive for the simple scenario that, okay, there is heat source in the core, and there was an early paper by Thompson and Duncan in the mid-90s where they basically speculated that, yes, magnetars have internal temperature of 10 to the 9th Kelvin, and there is self-regulation, kind of self-regulation of their luminosity to 10 to the 35 ergs per second. There is a problem with that, though. But before I talk about this problem, let me explain what is the heat source in the core. What is the possible heat source? There are not many choices. There is one process that can possibly can be efficient in heating the core of the neutron star, and that's ambipolar diffusion. Ambipolar diffusion is a process of motion of electron and proton component through neutrons. So the core is mostly made of neutrons, and the magnetic field and electrons and protons, the charged component of the core, are coupled together. This is a very good conductor. And in principle, they can move through the neutron background. They actually would like to move because there is Lorentz force that acts on electrons and protons in the charged component. J cross B force, right? The Lorentz force. There must be J, because otherwise you don't have magnetic field in the star. So somewhere there must be electric current circulating in the core. And of course there is B.
The equations are invisible.
I kind of know that, so I'm trying to compensate for that, but making it more tail-like. I don't know. I can write them. There's no hurry, right? So we have an hour. So I'll write this. That's enough for this equation. So the bonus that I can write even more equations. So one would be, which you certainly know, is a relation between curl B and J, right? It's the Maxwell equation. So 4 pi over C times J is curl B. Neglecting displacement current, there is no evolution. Electric field. I mean, there is evolution, but this term is very slow. Its evolution is very slow. Now, J cross B force, that's the Lorentz force that is applied to the charge component. Right, so you can plug in here J, and then you get the equation that is written there. So it's curl B cross B over 4 pi, right? That's the Lorentz force. And so it can be, well, you think about other forces that can act on the charge component, and they have to be in balance almost, right? So this one force, it's equal to the pressure gradient term, which I'll write in a strange form, but I'm going to neglect it anyway. I'll explain it in a second. And then there is so one force is the Lorentz force. This is the force that comes from possible pressure gradient in the star. Not exactly, because there's hydrostatic balance here, which is subtracted from this equation. And also, there is a friction force that acts on the charge component because protons collide with neutrons, right? So that's the friction force. And you can write, I will write it in terms of characteristic time scale of collisions. So it's going to be simply the momentum density over the time scale of Pn collisions. So that's the equation for ambipolar diffusion. This term, delta mu, well, it's a fancy way to write whatever the pressure gradient effect is for this equation. It's the mismatch between chemical potentials of electrons, protons, and neutrons. So normally, when you look at the core, basically what you have in the core, if you forget about muons and some unclear stuff at very high densities in the very center, you have electrons, protons, and neutrons. They're all degenerate, so they fill up their level, up to thermal level. And in equilibrium, you have chemical equilibrium. In principle, you can convert electron and proton into neutron and back in principle. So imagine this reaction. So when you have reactions that maintain this equilibrium, the sum of electron and proton chemical potentials have to be equal to the neutron chemical potential. That's chemical equilibrium. So if you're in the equilibrium, this term is 0, and you don't have this. And what you have for the evolution is the simple balance between J cross B force. So basically, the magnetic field sits in the star, tries to relax, to lower its energy, and move through the neutron background. But it feels friction. It's not so easy because it's frozen into electron-proton plasma. And as it tries to move, because of proton collisions with neutrons, they feel like it's very strong drag. So it's very viscous flow, like in honey, trying to move, to stretch your arms, essentially. And it's very, very hard. So this process works slowly because of that viscosity, because of that friction. Now, this thing tends to be erased by neutrino. So the conversion of electron and proton into neutron and back is assisted by neutrino emission. And so it's sensitive to temperature. If the temperature is high enough, then this delta mu is erased quickly, and you can neglect it. And for most interesting initial stage, that's a good approximation to say that this term is 0. Then you have very simple bonds that you can study in more detail and obtain exact solutions, etc. Now, there was a recent paper by Pengier and Gusakov in St. Petersburg where they actually argue that maybe the assumption that the classical papers made, like Goldreich in June, the reference there that you don't see anyway, 1992, that paper and subsequent papers made the assumption that the neutron component is static in the core. It's the heaviest. Yeah.
Sorry, why isn't the neutrino chemical potential included in that balance?
Why can't, say it again, why can neutrino?
Why isn't the neutrino chemical potential included in that?
It's not included because they can escape easily.
Okay,
Yeah. But you're right, in principle, when you write the reaction, you have electron plus proton goes to neutron plus neutrino. So if you write the chemical balance, it would be chemical potential for electron plus chemical potential of proton is equal to chemical potential of neutrons plus chemical potential of neutrinos. But you set the last one to 0 because they escape. They don't stay there. Okay. Now, that recent paper argued that maybe actually neutrons are dragged into that motion also. So this viscosity also drags neutrons with them. And maybe it's actually the main component of velocity. It's not completely clear to me yet. It might be right. But anyway, in the simplest model, you have static neutrons, and the magnetic field is trying to move through. Now, this is clearly a dissipative process because you have friction, right? These collisions, it's essentially a friction mechanism. So it's dissipative. It generates heat. And you can calculate how much heat you generate. You just take kinetic energy density. Well, first of all, you can find velocity from here, right? Just equating these two terms, you know tau Pn. Since you don't see any equation, I can write it. I maybe have it somewhere. No, too bad. Well, I think one thing I remember is that it scales with temperature in such a way, it scales with temperature squared. So if temperature is very high, the collisions are frequent. Okay, so the time scale is short. Temperature to the -2. The reason for that is very simple. You deal with degenerate particles. And so when temperature is 0, their free path is very large. So protons and neutrons don't collide very frequently because all the states are occupied in completely degenerate gas. And so the free path for collisions is very long. If you heat up a little bit, well, it will be 10 to the 9th Kelvin, it's not a such small temperature, then you open up some states. And therefore, collisions become possible. Now you have final states for a proton to go to, right? Because you open some states below the Fermi level. And so the higher the temperature, the more states you open and the more frequent the collisions become. And that means, the more frequent collisions, that means that you have more friction, right? All right. So this term is sensitive to temperature, and therefore the velocity that you obtain by balancing these two forces is sensitive to temperature. If the temperature is high, the velocity is small. That means that kinetic energy density, rho v square over 2, is just mass density of the proton and electron component, is small when the temperature is high. Now, then you can divide this over the characteristic time scale dissipation of collisions, and then you get the heating rate. So basically what's happening, you have a proton moving with this velocity, boom, colliding against electron, losing its momentum. That's how much energy you dissipated, right? So the point is that all these equations are quite simple, and you can plug in it in a more detailed model and calculate it and find the result. So one more ingredient that you need to have is because the collision rate is sensitive to temperature, you have to calculate the temperature self-consistently, right? So you have to solve the equation, the thermal balance equation. Heat capacity of the core per unit volume times the time derivative of its temperature is equal to the, let's call it, heating rate minus, if you have any cooling, you have neutrino cooling rate. Okay, so that's the equation for the evolution of the core temperature. So what's happening is that magnetic field is slowly moving through the through the core, and it heats it, and at the same time you radiate this energy away, and then you find a balance between heating and cooling. So it turns out that this system, for a long time after the magnetar birth, finds a temperature at which these two terms nearly balance each other. And you can calculate this equilibrium temperature, and you can calculate how long the core will stay at that temperature. Well, that's basically controlled by how much energy you have free energy you have in the magnetic field, and with what rate you're trying to deplete it. Once you deplete it, a significant fraction of that available magnetic energy, well, your process stalls, and you continue different evolution. All right. Do you see anything there? That's the equation for T-balance. I kind of lazy to write all the equations. Oh, you see beautiful red box, right? What is inside the box? What is written in the box is, okay, it's T-balance is 8 to 9, 10 to the 8th Kelvin, and then there is some scaling factor which depends on the magnetic field, expressed in units of 10 to the 16th Gauss, and also divided over L5. L is a characteristic scale of variation of the magnetic field. Obviously, you have gradients of magnetic field entering that equation. So the velocity of ambipolar diffusion is controlled not just by the value of B, but curl B as well. So there is a gradient of B that depends on the scale of variation of B. That's scale L. But for characteristic value of that scale, let's say 1 kilometer, which is 1/10 of the core, you can estimate the temperature, and you find that the balance temperature is somewhat below 10 to the 9th Kelvin if your field is about 10 to the 16th Gauss. The scaling with the field strength is 0.2. So it's B times delta B, the variation of B, over L to the 0.2 power. So it's rather slow scaling. You naturally get the right temperature. That's the point. Okay? The only problem is that when you calculate the time over which you have this balance, especially if you make more detailed calculation, this time is not very long. It's actually typically shorter than 1 kiloyear. And it looks, what we find by doing this calculation is that it's a bit difficult to actually make this time longer because, okay, naively you would think, let me just assume even stronger magnetic field. I have more energy to dissipate. Maybe I can keep the star hot longer. But in fact, when you have stronger fields, then the ambipolar diffusion becomes faster. Yes, you produce more heat, but you do this, faster, and in the end, still the time scale is short. That's what happens. So it looks like for this system, for this mechanism of heating the core of neutron star is quite hard to obtain a hot magnetar with age significantly longer than 1 kiloyear, and we see magnetars up to 10 kiloyear in age. That's illustrated by this plot, which I'm sure you don't see, but it basically, actually you can see there is a green square, which is where the data are. And the three curves, you can see at this point that, okay, black curve, this is the upper curve, number 3. You have strong heating, strong field, but, okay, it decays early. And you can have longer, red curve, longer heating with weaker fields, but it's still, you never reach this green square where actually the observed magnetars are. One interesting point which I would like to make, and actually I'll ask you this question. There's a nice, simplest, let's say, one-dimensional formulation for this ambipolar diffusion problem. You can see the sine curve, right? So what is shown there is the simplest one-dimensional magnetic configuration where you have a magnetic field depending on only one coordinate x, and the field is, let's say, along the z-axis, and it changes, varies with x as a sine. Okay, just a periodic sine wave. And that's the initial state. Now, there are a couple of equations which are written there in this, for this particular one-dimensional setup. You can rewrite this term, and obviously there will be only ddx operators because nothing depends on y or z. You know, it's like slab geometry essentially, one-dimensional plane parallel geometry. And so the equations would be, one equation is, well, I'll write to you, and you will tell me what's the meaning. So b would be 0, 0, b. b is in the x direction, and b will be a function of x, and b of x is some b naught times sine kx. There will be equation number 1, and there will be equation number 2. That's this one, which is expression for velocity. No, tau has to be upstairs. Rho p over tau, which depends on temperature. This operator is basically a way to rewrite this term, okay, for this one-dimensional geometry. You can imagine that when you have field that depends, which is in the z direction and depends on x, you can easily write down the value for this curl. Then you take the cross product of the curl with b along the z-axis, and you end up basically with this expression, dx of b squared over 8 pi. So that's the second equation. What's the meaning of the first equation? Do you recognize this one? Induction. Usually it's called flux freezing condition. This is ideal conductor condition, right? It basically tells you that the magnetic field is frozen into, it's a version of induction equation which expresses the flux freezing. The magnetic field is tied, magnetic field lines are tied to the electron-proton plasma, okay, and moving together with it with velocity v. And v is set by this balance of forces between friction and Lorentz force. Yeah, so if I start with this sine profile, here's a question to you then. What do you think will happen if you just let it relax with sine profile? I can draw it again here. This is 0, and you have a profile like this. How it's going to evolve? Why unstable?
Because there is minus sign.
It's opposite to gradient. No, I mean, what's happening here, you can think of it as gradient of magnetic pressure. So the velocity is such that the gradient is like negative gradient of pressure in hydrodynamics. Magnetic pressure pushes stuff away from the maximum of magnetic pressure. That's all that is happening. So what the magnetic field would like to do here is just redistribute itself so that there is less gradient, if you like.
The time evolution of B is directly proportional to B itself.
Yes.
So at the beginning the evolution will be faster than
Yeah.
less methodically time to equality.
Right. Do you see any special points, by the way, here? 0, yeah, where B is 0. Right, when you take this operator, you can write it as B dxB over 4 pi, right? So we're at the point where B is 0, nothing is going to move. So these points are fixed.
So it would probably be a step function.
Yes, right. So there are two things that are happening here. Right, so one is the flux conservation. This expression basically tells you that the flux, that magnetic flux is conserved. The other thing that is happening, the system is trying to lower the magnetic energy, right, through dissipation. So this is a constrained evolution with fixed flux, so that flux is conserved, and a way to lower energy is basically this. So you create a discontinuity in the end of it. You create a current sheet. Right? The system will push this excess of magnetic field to the side, and it flattens here completely. But here, the price is that you have a steep gradient. So you create a current sheet. Now, current sheet, of course, means that even small resistivity, however small it is, will at some point would become important, and you would have some dissipation. Because the dissipation rate is J square over sigma, right, per unit volume. So when it scales as current density squared. And so when you have strong current, current is proportional to gradient of B. As it steepens more and more, this gradient is growing. So the current density becomes very high. And the dissipation rate becomes high. So there is a natural way for ambipolar diffusion to form current sheets. It's just a simple setup, but it's this kind of general argument. Even for 3D configuration, you find that similar conclusion holds that this relaxation tends to form discontinuities, current sheets in this term. Yeah.
The discontinuities require zero magnetic field.
In this simplest case, yes. But in the general 3D configuration, I don't think you need 0. You can create jumps of one component with some guide field, and you can have jump of the other component. All right. So ohmic heating, I'm not going to write these formulas. The point here is quite simple. We sort of know what's the conductivity, and you can calculate. Ohmic heating is another possible source of heat for the star, right? So if ohmic heating becomes significant, maybe you can heat up the core to 10 to the 9th Kelvin. So the answer is no. The conductivity is too high, and you cannot really produce enough heat in the core. Maybe it is an interesting source of heat in the crust, especially in the upper crust. For that, you would need, again, obviously, very strong current density, J. So you need very large curl B. So if you have structures in the crust where the magnetic field changes by 10 to the 16th Gauss, delta B of 10 to the 16th Gauss, over a scale like 100 meters, or less than 1 kilometer, let's say, then the ohmic dissipation can become important. And in principle, it could supply this 10 to the 35 Earth per second heat power. But it's a kind of extreme assumptions, right? So it's not, in principle, possible, but seems unlikely. Okay, so the next important, and actually the other important process of magnetic field evolution in a neutron star is Hall drift. And by the way, you've heard about both ambipolar diffusion and Hall drift from Phil Armitage, so I hope some of it is familiar already. But it's just different system. Things are happening slow here. The Hall drift in particular is very slow, simply because the densities are very high. Now, what is the Hall drift? Just let me remind you. The Hall drift is the motion of magnetic field lines together with the electrons with respect to the protons. So let's not be confused here again. Ambipolar, the important aspect of neutron stars is that it has interesting composition. You have different fluids: electron fluid, proton fluid, neutron fluid. And so in principle, you can have magnetic field lines moving together with electron-proton plasma with respect to neutrons. Or if you look more carefully, you will find that actually the magnetic field lines are frozen into the electron component, which could in principle move with respect to the proton component. Now, why it's frozen mostly in the electron component? That's because, well, you tell me, why? You've heard from Phil. Did he explain why the magnetic, why it's right to assume that the magnetic field is frozen into electron component rather than proton, let's say? What's the key factor there? What's the difference between electron and proton? Mass, yeah. So electrons essentially have no inertia compared to protons. So they don't tolerate electric field, which would accelerate them. So basically the electric field has to be zero in the rest frame of the electron gas. And so then you can write the condition that E plus V electron cross B, that's how you transform the electric field from the lob frame to the rest frame of the electron flow. And electrons are flowing because they conduct current in the crust. They flow actually through the ion lattice, right? This field in the electron rest frame must be zero. Then you simply plug in this into the induction equation. Right? It's one of the Maxwell equations. And then you find that you find the same equation as I wrote there at some point here. But now more specifically, you can see that it's actually electron velocity. So if you treat it as electrons and protons in a single fluid, you can simply write the V. But if you want to focus on the possible relative motion of electrons and protons, it's actually more precise to write electron velocity. Now in the crust, in the rigid crust, ions are not moving. They sit in the lattice. An electric current, which could be there, curl B may not be zero, is conducted by the electron fluid, which are flowing through the crust, and they are advecting the field lines. That's the whole drift. That's it. Yeah.
One question about the question.
Uh-huh.
This also, I mean, this depends on the ion scheme depth, I mean, on the length scale when you're already studying the work, which is defined. I mean, this will be valid if your length scale is smaller than the ion scheme depth, which is the inertia of the.
No, the skin depth is minuscule, right? Because the densities we're talking about are like electron density, let's say 10 to the 35 particles per centimeter cube.
So
right?
The function of the length scale and the density is a combination of the two scales.
I'm sorry, I don't get your question.
When you divide the induction equation and using this kind of approximation.
Uh-huh. Which kind of approximation? The initial equation just is the Maxwell equation. Uh-huh.
I guess that depends on the length scale of your problem. That the length scale has to be smaller than the inertial scale of the ion, and that depends on the ionization that you have in the middle. If it's weakly ionizing or strongly ionizing, that will change.
Weakly ionized. So this is completely ionized stuff. So we're talking about, it's very simple. We don't need this complication, right? So what you have here is a piece of metal, essentially. Okay? So it has huge density, by the way. It's a perfectly conducting medium. All the normal plasma, I know what you think about. You probably think about dilute plasma, let's say in planetary disks or somewhere else, where you have to think about scales. Like here you have gyroscale, which is minuscule, you can calculate it. You have skin depth, which is minuscule because of high densities. And so all you have here is dense electron gas flowing through the fixed lattice. Ions are not moving. So there's no issue with the, the issue that I think your question hints about is that maybe ions are moving, and it's not happening here. They sit in the lattice.
But we're moving another scale.
So the ions are sitting in the Coulomb lattice. They are just nailed. Okay, they found the equilibrium position, and just electrons are drifting through the lattice. That's all that is happening. The induction equation is exact, and that's the electric field that is felt by the electrons in their rest frame. That's it. There's nothing else here. Just you express electric field from here, plug in into this equation, and immediately arrive here. That's it. Okay, so you can calculate the time scale for this process to work. And this time scale is going to be proportional to, well, obviously to this electron velocity. So what is it? The electron velocity is the electric current, which is carried by electrons, and just divided by charge and electron density, right? So current is electric charge, that's number density of electrons times velocity. So you can see that this velocity is, of course, inversely proportional to density. It's small, and therefore the time scale, how long it takes for the electrons to transport the field lines, is very long. If you plug in numbers, you get time scales of like kiloyear, thousands of years for typical densities, typical magnetic fields. Of course, it also depends on the magnetic field. Okay, that's the Hall drift. There is also such a thing as Hall waves, which are analogous to Whistler's in plasma physics. I don't know if did you see Whistler discussion last week? Okay, so that's when you look at this equation, you can study waves that this equation would support if you consider, for example, the simplest configuration like this. That's background magnetic field along the z-axis. Then there is some perpendicular component of the magnetic field, which is going to depend on time. And again, it's one-dimensional system. Things depend on z in this case, and they don't depend on the two coordinates in the horizontal plane. So that would be your field, which is not changed, B naught. And then you can rewrite this equation for B perp in a nice form, and then you will see that this equation supports a wave with a certain dispersion relation. And this dispersion relation is going to be, it's written up there, but you cannot see, right? So omega of the wave is proportional to k squared, the wave vector. So dh, the coefficient of proportionality, the Hall coefficient, is c times bz, that field, the background field, divided by 4 pi e and number density. It's the same as what they call Whistler in plasma physics, because what happens in Whistlers, when you have lightning, for example, in one hemisphere, and you imagine dipole field of the Earth, that's the mode that propagates at such frequencies that does not touch ions very much, so it's sufficiently high frequency. And so ions don't move, and electrons move according to the current that is conducted by the wave. And so that's basically the same situation. But here you have metal, much higher densities, ions don't move, and electrons are moving together with the current. And so it's known as Whistler, where they call Whistlers because when it comes to the other foot point of the magnetic field, the other hemisphere, you see this little whistle. It has the characteristic, from this dispersion relation, you can find it's how velocity of the wave depends on k, okay? And you will see that the high frequency modes, high k modes, propagate faster, right? You can see this from here. Omega divided by k is proportional to k. So the phase speed of the wave is proportional to k. Also, the group speed of the wave is proportional to k. So that means high K waves propagate faster, and then you first receive the high pitch signal, and then it's whistling. So the same thing is happening with the Hall waves, just different name for essentially the same wave. Well, these are really nice plots that Xinyu Li, a student at Columbia, plotted in a paper, and I'm so sorry you cannot see them. Visible? The red is visible. So it's the spiral like this. So what it shows, you see the lower plot anyway, right? Crust, core. So it shows a simple situation that would lead to excitation of such a Hall wave in the crust. If you imagine a slab, let's say of rigid material, where you try to launch the Hall wave, and below it you have the crust, and something happened quickly in the crust. There was bipolar diffusion, the field has evolved, it dragged the field line somehow, but the field remained frozen in the crust. There was no Hall, there's no bipolar diffusion, there was no Hall effect yet. So what happens then generally is that you create a kink between the field lines in the crust and the field lines in the core. Now this kink implies that one of the magnetic field components, in particular the horizontal component, jumps. So there must be current sheet screening this jump on the field. So if you imagine this scenario where, well, probably that works this way, inside the neutron star core, the field has evolved, leading to current sheet creation at the interface between the core and the crust. This current sheet is going to launch a Hall wave into the crust. And the way, you can solve exactly this problem. You take this, let's say vertical in the simplest configuration, the vertical magnetic field in the crust, then you imagine here a kink in the field line, so the jump in B perp essentially, that's your initial condition, plug it into the equation and you can solve it. What you find is what you should expect from this dispersion relation is that this jump, when you do the Fourier decomposition, it contains all modes, right, the entire spectrum. Delta function has a flat spectrum, essentially. And these modes will propagate with different speeds. And first you launch high K modes, and then low K. And so that's what you see kind of in this. You see the leading waves are shorter, and the trailing waves are longer. And so you launch this trail of waves into the crust. And one interesting thing that and these waves are circularly polarized. The nice equations that you could not see on the previous slide actually explicitly show that the equations are for circularly polarized wave. This wave is circularly polarized. So it goes, electric field in the wave rotates like this. And that's why this red curve, which is essentially the curve, traces the endpoint of this B perp vector. So you start with just this point, and as the wave launched, this B perp is moving like that, and this red curve traces the end of B perp. When this wave is launched into the crust, you create magnetic stresses in the crust. And so the crust can break because of these stresses. Now, magnetic stress is basically the product of, well, what is the stress? Stress is the flux of momentum. So the stress is flux of momentum. If you think of, let's say, x momentum flowing in the z direction, then the stress would be basically bx, bz. So if you have b perp and you have background bz, that's the condition for this momentum flux to flow. That's the stress, yeah?
5 minutes.
Okay, good. So this stress has to be offset. Basically, this stress is applied to the rigid lattice, and you deform it elastically. If this deformation is too big, the crust will yield, and it will begin to move. That's what's happening with magnetars. The crusts actually are not static. They can be. We know that they move, right? So I showed you the evidence for the evolving external magnetic field that is attached to the crust. So we think the surfaces of the stars actually moving. Why they are moving? Because there are these magnetic stresses that are developing, in particular in the crust. And these stresses are strong enough to actually break the crust and move it. For that, the field has to be strong enough. So that those fields, 10 to the 15th and higher, are actually capable of breaking the crust and moving it around. How can this crust break? Well, there are not so many options because, well, naively, if you take this and break it, right? So you create a crack. So what is a crack? A crack is a void that is created first in the material, and then this void is growing. That's the usual way of breaking material. Now, this cannot happen in Newton star crust because it's under huge pressure in hydrostatic equilibrium. So material is very strongly compressed. There's no way of creating the void. Also, remember that when you are trying to break the crust, what we mean by breaking the crust, we are breaking the lattice, the ion component. So what we are rearranging the position of the ions from its regular, normal initial configuration in the lattice. So the lattice begins to move. So we are working against Coulomb interactions between different ions in the lattice, which is much smaller. This Coulomb energy density is much smaller than the hydrostatic pressure in the crust, energy density in the degenerate electrons in particular that maintain the pressure. So the crust is a kind of floating in this highly pressurized electron gas. And the easiest way to break it is to create a shear. It's very hard to compress it, but if you create a shear, you can easier to break it. So anyway, cracks are not an option. It's not easy to make faults like sliding planes because the crust is magnetized, right? So the crust is threaded by magnetic field lines, and so if you try to shear, immediately, that's what's shown in that plot, the red curves are the magnetic field lines. You would shear the field lines and actually generate an enormous component, a horizontal component of the magnetic field. You would increase the magnetic field energy by this sliding. While what the system is attempting to achieve, of course, the primary reason, the original reason why the crust would break is, of course, that the magnetic field would like to relax, right? Because the tension that develops and the stresses that develop in the crust, they develop because the magnetic field is unhappy. It's trying to relax to low energy configurations. So it doesn't seem plausible either. So the most plausible way of thinking about how the crust would yield is that the magnetic field lines relax to a new configuration by initiating a plastic flow, okay, which is growing in volume. And that's the picture. So before the lunch break, I guess I will stop after this slide. That's the picture that shows how this wave would be generated in the simplest geometry. Right? What you hopefully see there, red is the magnetic field line. There is dotted red, which is the initial field line. So basically you have field line above the crust like this, and then you have field line into the crust like this. So here you have the stress because you have both horizontal and vertical component of the magnetic field line, of the magnetic field. And so at some point, let's say somewhere in a layer, in the simplest one-dimensional geometries, in a layer in the crust, this stress exceeds the critical stress, after which the crust says, okay, I'm no longer solid. I'm going to yield and flow plastically. The field is too strong for me. And so it begins to flow. Once it begins to flow plastically, it generates heat, because plastic flow is a dissipative process. It generates heat. The heated crust becomes softer, weaker. So if you manage to break a colder crust, certainly it's much easier to continue moving the hot crust. And now what happens next, it's very similar to deflagration wave in combustion physics. So when you generate this heat begins to be conducted to the next layer around this yielding plastic flow layer. And that layer becomes softer, and it yields too. And then you light up, it begins to generate heat too. And you generate two fronts of deflagration that propagate away from this initial trigger point. And what they do basically, as this front propagates, this thermoplastic wave converts the horizontal magnetic field energy into heat. Okay? So what you see here with the solid line is basically, you see in the green burned region, let's say, where which is hot, where the waves already pass through, the horizontal component of the field is reduced. The field is more vertical. And that means that you have released the magnetic energy, converted it to heat. Yeah, let's keep that. Yeah.
What represents the fluid velocity in this case?
The fluid velocity?
Because the momentum equation.
That's a good question. Yeah, so the flux freezing condition is still satisfied. So it's still a very good conductor. And on the time scales which are over which this thermoplastic wave works, these are relatively short time scales compared to Hall drift or anything. So when you see the motion of the field line, it actually reflects the motion of the material it is frozen into. So what's happening there is that this green layer is where you essentially allow sliding of the upper plate of the crust relative to the lower plate. So essentially what's happening, you have strings, the magnetic field lines, that go through the crust. You pull, and you try to break it, try to slide this way. And at some depth, at some point, it yields. And this upper slab begins to move. So that it's not exactly this pull, like I said, you have, but anyway, so it's close enough. So basically you have, you allow one slab to move with respect to the other. That's why you see that shift. You see the kink in the red curve. That's because that slab, it moved in this velocity Vc is the crust speed. The upper slab is moving. And that's, by the way, why you also expect the magnetic external field to change, because since this surface is moving, whatever field lines are attached to the surface are going to be moving too, right? Because they're attached to the moving crust. And that's the basic mechanism that eventually leads to stuff I will discuss after the lunch break, is how we create giant flares that we observe. Because in the end, the most interesting dramatic phenomena that we see, they come from the magnetosphere. And the magnetosphere, like solar flares, reflects the motions, the subsurface dynamics. So when the surface is moving because of effects like this, then the magnetospheric field is evolving and comes to an unstable point and generates a flare. Okay. All right, I should stop now, and then we'll continue. Or maybe we should have, okay, you have any questions before I have like, yeah.
I don't know if you said this already or not, but what kind of lattice structure are you expecting? Like what kind of packing scheme?
I think BCC is like normal. Yeah, I'm not sure actually. It's like regular. It depends also on what kind of ions you have, I think. Yeah, no, it probably stays like lattice. Yeah. There's a big uncertainty actually what happens in this plastic region and what is the effective viscosity of that flow. You could, in principle, completely melt the material. If the magnetic field is strong enough, the field that you dissipate, the horizontal component, you release enough energy to completely melt it. Then, okay, you just get rid of the crust of the lattice structure altogether in that layer. But of course, later it cools down. What happens next? The heat diffuses from that region down to the core, also to the surface. And this energy mostly is converted to neutrino emission actually, and is radiated from the core. And a fraction, like a few percent, 10%, goes to the surface and is radiated away. So the region cools down and crystallizes again. But for that you need rather, it's possible, it depends on the strength of the field that you dissipate. You can even melt it. Yeah.
So I'm not sure if you mentioned it or not, but the conditions for so we have the magnetic tension in the field lines, but the crust has some tension also. So what kind of, would these, you're going to speak about those flares later, but would they happen in every situation where this magnetic field wants to relax, or is there some ratio between the field lines?
So what happens in the crust is basically a stress balance between the elastic stress and the magnetic stress. It's like normal deformation in the metal. If you apply some stress from outside, let's say, and it doesn't want to move, it just deform it a little bit and found in equilibrium, you find a mechanical balance that you can calculate. What's important for the flares is the net motion of the surface of the star that you can see from outside. This is the motion that the external field lines feel, right? So if you have a field line with two foot points attached to the star, and these foot points are moving, well, your magnetic configuration is going to change. In particular, you can twist the field lines. That's what is important for giant flares. And of course, to explain the spectrum in particular of giant flares, the energy release has to occur in the magnetosphere, not below the surface. Right, so that's why you have to think about how this energy is extracted from the core, deposited into the magnetosphere, and then it's dissipated, converted to radiation there. So the extraction from the core is achieved through the Poynting flux. If you have the surface layer pulled by these internal processes, so the surface crustal material is moving, for example, you're twisting up the external fields, what it means basically is that there is Poynting flux that transports magnetic energy from the interior to the exterior of the star. E cross B flux that you can think of as V cross B. If you have some non-zero velocity, that this velocity implies some Poynting flux into the magnetospheres. Not much different from the case of pulses that I discussed yesterday. There you have rotation, and the V cross B induces electric field, and you have Poynting flux flowing from the star and partially dissipating into the magnetosphere. Same thing is happening here, but much slower, because these velocities are not rotational velocities. These are plastic flow velocities, which gradually extract magnetic energy, but they gradually change the external configuration so that ultimately it becomes unstable and generates a giant flare. Yeah.
Going back to Alex's question, if you break a crust and it recrystallizes into the lattice again, is it possible for that to number one, retain a memory of breaking and be like affect the lattice in some way, and number two, would that even be dynamically important?
Good question. I don't know. Would it be possible, observationally, you mean, to see what effect of breaking, what kind of long-term effect of the breaking would be on the crust? That's your question, right? After it heals. I don't know. It's not obvious how you would. I don't think you can change the composition. When it heals, it becomes again the same lattice. The only thing that is changed is the magnetic field configuration, I think, ultimately. And of course, the heat. The main effect that you see is just the heat flux from that region. I don't think you can see any change in material itself, and it would not be any observable consequences, I think, of that. All right, should we have a break now? Then lunch break. Okay.